Hey there, everybody. Today we're going to be doing the 25th question from the 2016 AMC8. So let's take a look here at this question. A semicircle is inscribed in an isosceles triangle with base 16 and height 15, so that the diameter of the semicircle is contained in the base of the triangle as shown. What is the radius of the semicircle? So this is a common advice I'll probably give for almost any geometry question, but since this exam entails like an actual paper where the diagram is obviously much smaller than I have on my screen, it's nice to redraw the diagram, make it a little bit bigger. I know, it doesn't look completely isosceles, so just exaggerate it a little bit. Okay, it's not perfect, but it'll suffice. Okay, yeah, that's good enough. Okay, so let's first input the given information into our diagram. So let's just start labeling stuff. So first, let's draw this height because it gives us the height, so we should use all the information we're given. So we know that's 15. Let's not label that for now, but let's say it's 8. This is 8 because the base is 16, and when you draw the altitude like that in an isosceles triangle, this triangle over here and this triangle over here are obviously congruent just by merit of symmetry. Oh, sorry. Okay, so you don't know that the height is 15. Okay. Yeah. Let's not get confused. As there is this portion here, so let's just not confuse that as 15. The whole height here is 15. Okay. So actually, I'm gonna put that somewhere like in the middle here. Okay. Yeah. You don't want to get confused by your own diagram. So that's gonna be 15, and we know this is the right triangle. So what else can we figure out in this diagram? Well, we have a right triangle. We have two legs, so we can find out the length of the hypotenuse, which is one of the sides of the isosceles triangle. So let's try to find that out, and we're going to use Pythagorean theorem here. So the hypotenuse, let's just say that's c squared equals 8 squared plus 15 squared. Now, if you do not know your Pythagorean triples, you can just compute this. So 8 squared is 64. 15 squared. It's nice to memorize your perfect squares from like 1 to 20-ish at least, because it's especially helpful for Pythagorean triple problems where you don't know the actual triple. So this comes out to 289. So c squared is 289, and thus c equals 17. Yeah, so you don't have to know that 17 squared is 289 in this case. Okay, so we know that 17 is now the hypotenuse here. Now let's just quickly look back at the question. So it's asking for what is the radius of the semicircle. Okay, so if we're trying to find the radius of the semicircle, we gotta actually draw the radius in some point in this diagram. And now we just gotta figure out which would be the most beneficial place to do this. So we know the center obviously is here. That was given to us. Okay, just by the merit of symmetry. Okay. So there's a couple of places we can draw the radius. We could draw it, of course, there's obviously already one drawn here. But is that really going to help us? I mean, there's not too much we can really get from there. We don't really have another option or any formula to really try from there. So this might be a novel technique, but what we're going to do here is draw an additional line, or you can call it an auxiliary line, but basically we're going to draw a radius from the center, which is obviously on the base, to the tangent point over here. Let me make that tangent. Now you might not know this, but at that point of tangency, the radius and the line which that radius is, which a circle is tangent to, that constitutes a right angle. So you have a right angle over there. And you have one over here as well, just by the merit of symmetry. But it doesn't really matter, because now we don't really need the semicircle, if you think about it. So let me just redraw this diagram for a second, just to show why we really don't need the semicircle. And let me put some labels in this. Sometimes nice to label your diagram with A, B, C, and all that. So let's put A, B here, C here. Let's call this O, and we call it O just as a standard designation for a circle. It's the center of a circle. In this case, it's a semicircle, but that still applies. Okay, so we have that. Now we know that this is the radius which we're looking for over here. So let's call it R. It's nice to name it that. It's a good variable. Okay, we know that this is 15. We know that this is 8. And we know that this is hypotenuse. And we know that this is the right angle. So all we need to do, and we also know that obviously this is also a right angle. So we really don't need the semicircle. It's not exactly helpful at all. So let's just quickly get that out of our diagram. What we really need to focus on, we don't even need this side at all, because it's just going to be symmetry anyways. All we need is this triangle over here, AOC, triangle AOC. Okay. So basically what we're trying to do is, the problem is basically simplified to finding the altitude from the vertex B, where the right angle is at, to the hypotenuse. And this is a very classic question. So there's a couple of ways of doing this, and I'm going to show the simplest way in here, but I'm going to suggest a few other ways in a moment. What we can do here is think about the different characteristics of triangles. So all triangles have the characteristics of like perimeter and area, of course. All polygons really have that. So in this case, we're going to look at the area and see if there's anything special about it. You see, it's always nice to look at defined qualities. Like in this case, we know the two legs, and since they make a right angle, the area here is just 15 times 8 divided by 2. Okay? Now, what happens if we rotate this triangle? So I'm going to give some more space for us here, so we can redraw this triangle. So now we're going to rotate the triangle in this redrawing, and we're going to put O here. Okay, let me just quickly check. Yes, this is C, and this is A. We have a right angle here. This is the radius we're looking for. This is going to be 17. This is 8, and this is 15. Now from this perspective, the base and the height are different, because in the last example, let's just quickly look at that again. OC is considered our base, and OA is our height, so just half times base times height, that's going to be our area. But in this case, since we rotated it, the new base is 17. And our height is actually the radius we're looking for. So from here we say that 15 times 8, which is 120, is equal to 17R. And thus R is equal to 120 divided by 17. Okay? So that's our final answer. And the answer to this question is B. So basically the key to solving this question was equating two quantities, one which is defined, 15 times 8 divided by 2, which is the area of course, but equating that to something which entails our variable. But another key step to remember was the idea of tangency, where the point here, the center, the segment drawn from that point to the point of tangency, which is a radius in this case, is perpendicular to that line which entails that point of tangency, this line over here. Okay. So the core concepts which we used in this problem were Pythagorean theorem. We also used the idea of tangency as well, a whole perpendicular idea. And we also use the idea of the area of a triangle, half times base times height, and we can shift that perspective. We can rotate it to make the hypotenuse the base, and the quantity we wanted here, the radius of the semicircle, the height in this case. And another way we could have done this is actually similarity, because all these triangles here, they're all right triangles. So, and they also have like common angles. So we call this like A. Let's not call it A. Let's call it let's call it theta. It's a Greek letter we sometimes use for angles. If you call that theta, then this is like 90 minus theta. And by similarity, which we'll go over in a subsequent video, these two angles, theta 90 minus theta, are found in every triangle. AO, let's call it H. Triangle AOH. Triangle AOC, the entire triangle, and triangle OHC, by a similarity called AA similarity, they're all similar. And they're not in this specific order, but they just are similar by merit of their shapes and the angles which constitute those shapes. So that's another way to do this. It's a little bit more time consuming. I wouldn't suggest this. So the area method is the way to go. Now you might think that this is a very innovative technique, but it's really not. So here's a couple of resources where you'll find very similar ideas. A couple of them are exactly the same application. A couple of the review problems over here. But generally, I'll ask you to look at chapter 6. Sorry, it says chapter 8 here, but it's actually chapter 6. So that's the right triangle chapter. And you can look specifically at the section 6.1, Pythagorean theorem. It goes over that. Also in 6.3, it goes over the Pythagorean triple. So if you memorize some of the Pythagorean triples, you'd have already found out the hypotenuse was 17 in like a couple of seconds. So yeah, just to quickly look at that, a couple of very important Pythagorean triples are 3, 4, 5. That's really the most important one, I think. 8, 15, 17. There's also 5, 12, 13. Sometimes 12, 35, 37. It sometimes comes up. 7, 24, 25. I think these are the most important ones. And I think the reason why some of these are the most important ones are because you can see some of the numbers are repeated, like 5 and then 2 of these, so that constitutes a problem. 12 is in some of these. It's also actually in 3, 4, 5, because also remember that the multiples of these Pythagorean triples are also Pythagorean triples in themselves, and we'll go over that in a separate Pythagorean triples video as well. But yeah, you'll need to know Pythagorean theorem for this problem, Pythagorean triples. These are some review problems, 6.43 and 6.49 specifically. Those go over the idea of equating the area to find the length of the altitude from the vertex with the right angle to the hypotenuse. So it's going to be the central idea that solves this problem. You can find those in those questions as well. And the whole idea of tangency, we'll probably go over it in another video as well, but it's beautifully explained in the Introduction to Geometry textbook at chapter 12, specifically chapter 12.3, and there's these conceptual problems, and 12.14, I believe, is the problem where they actually prove this. It's a little bit of an involved proof, But the central idea of tangency, which we used in this problem, the whole perpendicular idea, that is very well expounded on in that chapter. Now, another thing which we'll look at in some of these videos is what else could have appeared in this problem. Now, the first time I actually looked at this, I actually didn't take this contest. I think the contest which I took was the 2014 AMC 8, back when I was in 8th grade. That was the last one I took. This one actually surprised me because usually I actually found problems where they're asking for the radius of a circle instead of a semicircle. So actually the existence of a semicircle in this problem is quite helpful because it's a little bit easier. We just use the area idea. But that same area idea can be applied to the problem where we're looking for the radius of an inscribed circle. And that's called the in radius. And just another fun fact is that it's the intersection between the circle, the center of the circle, the incenter, also called, is the intersection between the angle bisectors. Okay, so let's call this A, this is B, and this is C. And by notation, we designate the length of BC to be A. This is opposite vertex A. We designate the length of the segment AC, which is opposite B, as little b. This is little c. Okay, so this is basically, this incenter is the intersection between the angle bisectors. And by that I mean, like, here's an angle bisector. Basically that angle is literally cut into half. So that line which does that which cuts it into half, the angle A, that's called an angle bisector. Similar thing over here, and another thing over here. And these lines, they correspond to, the equal number of lines basically corresponds to the angle being the same. That's another thing you might want to just make sure you know about the general idea of geometric notation. Okay, so how do we go about solving this problem? And we're going to do a general case like we're doing over here. We're just unspecified side lengths. We're not going to do the problem which you saw in the original AMCF problem. We're going to actually derive a formula for this, which you can later apply to similar questions. So we can draw the radius over here. And this is the application of the tangent idea. And that's basically the heart and soul of this, of deriving the formula for this specific problem, of finding the in radius of the circle that is inscribed in a triangle. So, oh, sorry, this is R. Okay, this is R, this is R, this is R. Okay, now we're going to do something similar here, just like we did in the previous part. So we're going to say that the area, okay, of this triangle is equal to the sum of different triangles in this. I'm going to highlight the triangles we're going to be talking about. So let's call this I, because I think that's the geometric designation for the incenter, or the incenter. So let's highlight this part, this triangle over here. Okay, we know the area of that is half times the base, and the base in this case we're going to say is C. Okay, so from that perspective, the height is R, just like we saw in the problem, the height was R. Now for this triangle, AIC, the base is B, while the height is R. And the final triangle, you'll probably see the pattern by now. It's half times A times R. Let me just highlight that for you, BIC. It's basically said that the area of, just reading this expression out, the area of the entire triangle is equal to the area of the individual triangles, these three individual triangles over here. which are separated by the angled bisectors. Okay, so let's take out, oh, sorry. Let's take out, let's factor out a half r from all these to get a plus b plus c. So that's basically our formula, but there's another quantity which we can define. It's not really a hard quantity to understand, but it's called the semi-perimeter, which is, as its name suggests, is half times the perimeter, or in this case, the perimeter is a plus b plus c. So a equals r, the radius of the incircle. Let's actually name it like that. Because also something called a circumcircle as well, a circumradius corresponding to that as well. And that's when you circumscribe a circle around a triangle where the triangle itself is inscribed in the circle instead of the circle being inscribed in the triangle. We won't talk about that in this video since it's a little bit too dissimilar from the original problem. But this is basically your formula for finding the incircle, the radius of a triangle. You can just use the semi-perimeter and the area, which are both pretty easy to do, usually at least for right triangles. If you don't have that, if it's not a right triangle, you just have the side lengths, you'll probably have to use something called Heron's formula, which we're also going to prove in a video. But for this video, basically just want to understand that the central idea of solving these problems, where you have like a circle inscribed in a triangle, or even a semicircle like in the original problem inscribed in a triangle, you have to use this area idea of somehow equating the area to very easily calculable quantities, which entail the variable that you're looking for. Okay, you gotta equate that area with those quantities, and you gotta also make sure to draw the radii. I think drawing the radii is probably the major first step. If you don't do that, you basically can't get the problem. So make sure to do that. I think that's a good suggestion for any tangent point. Basically draw the perpendicular radius, because that gives you another angle to include in your diagram. So yeah, that's all for this video, and I hope that's helpful. Thank you.